welcome you to this crucial deep dive. Today we are leaving the, let's say, simplified world of ideal gases, where molecules just kind of ignore each other,
Right.
and we're moving into the much more complex and powerful realm of highly reactive gas mixtures. We're talking about systems like hydrogen and oxygen, where there's a strong chemical affinity. A reaction is basically inevitable.
It is. And when you have that chemical affinity, the rules of the game change completely. You need a really rigorous way to define the state of equilibrium.
So that's our goal today.
Exactly. Our mission is to find that thermodynamic shortcut, the tool that lets us define equilibrium. And this is, it's absolutely foundational for material science.
Okay, so when you have these reactive gases, the sources mention two main paths you can take.
That's right. The first one is, well, it's technically correct, but people rarely use it. You treat the system as a super non-ideal mixture of the original components.
And you account for everything with fugacities, which sounds complicated.
It's mathematically brutal. So it's just way easier and more practical, especially at lower pressures, to assume the species have already reacted to some degree.
Ah, so you define the equilibrium based on what's actually in the container at that point.
Exactly.
Yeah.
Based on the partial pressures of all the components, the reactants, and the products. It just simplifies the physics into chemistry we can actually manage.
But no matter which path you take, the fundamental rule is the same, right, for a system at constant pressure and temperature?
The rule is unwavering. The system finds its equilibrium, its stable state, only when the total Gibbs free energy, G prime, hits its absolute lowest possible value.
Okay, let's use the generic reaction from the sources to unpack that. Say we have A plus B equals 2C, all in the gas phase, constant T and P.
Yeah.
We're looking for that one magic composition, the specific number of moles of A, B, and C that minimizes the total free energy.
Right. So to do that, first you have to define G prime at any given moment. And it's actually pretty simple. It's just the sum of the moles of each species, Ni, times its partial molar Gibbs free energy, Gi.
Which is also called the chemical potential.
The chemical potential, exactly. So G prime is just Na, plus Nb, Gb plus Nc, Dc.
And to find the minimum of that energy curve, we need to pull out the calculus. We're looking for the point where the slope is 0.
That's it. You're looking for where the incremental change in G prime with respect to the reaction is 0. So mathematically, you set the derivative partial G prime over partial Ni to 0.
And this is where the magic happens, because that big calculus step simplifies down a lot.
It really does. This is the elegance of thermodynamics. It simplifies right down to the core condition for chemical equilibrium. Ga plus Gb equals 2Gc. The chemical potential of the reactants equals that of the products.
Okay, wait, can you pause on that for a second? For anyone listening, that can feel like a bit of a sudden leap. How does setting a derivative to 0 immediately give us that perfect balance of chemical potentials?
That's a great question. The chemical potential, Gi, is by definition how the system's total free energy changes when you add or remove 1 mole of that species. So because the reaction stoichiometry links A and B being consumed to C being produced, the 0 derivative condition just means that for a tiny, tiny step along the reaction path forward or backward, the free energy change has to be 0.
So the driving force from the reactants is perfectly balanced by the driving force from the products.
It's a perfect balance.
Yeah.
A beautifully concise definition of equilibrium.
That makes sense. So now we have this abstract condition. How do we connect it back to things we can actually measure in a lab, like partial pressures?
We do that by using the standard state definition for chemical potential. So Gi equals Gi naught plus RT times the natural log of the partial pressure, Pi.
And you plug that back into our equilibrium condition.
We'll plug it back in, and it lets you connect those measurable partial pressures directly to the standard Gibbs free energy change for the whole reaction, delta G naught.
And the really critical thing that falls out of this is the equilibrium constant, KTP.
Correct. KPP is just the quotient of the equilibrium partial pressures, each raised to their stoichiometric power. For our A plus B equals 2C example, Kp is Pc squared over Pa times Pb.
Which gives us the single most important equation in chemical thermodynamics.
It really is. Delta G naught equals minus RT natural log of Kp.
And the immediate takeaway here, which is so important, is that because delta G naught is based on the pure gases in their standard state of 1 atmosphere, it's only a function of temperature.
Right.
Which means Kp is also only a function of temperature. The actual system pressure doesn't change the value of Kp.
Not at all. It's a fixed point of comparison.
Okay, to really understand how equilibrium works, we need to visualize what's making up that total Gibbs free energy change. It's a sum of two competing factors.
That is, imagine a graph. On the
Yeah.
vertical axis, you have the total Gibbs free energy change, delta G prime. And on the horizontal axis, you have the extent of the reaction, from pure reactants on the left to pure products on the right.
The first factor is the chemical reaction itself.
Right. And you can picture this as a straight line sloping downwards. Let's call it line 2. This is the energy decrease you get from forming more stable products. It's mostly about the enthalpy change, delta H.
So as the reaction goes on, this term just keeps driving the energy down.
Linearly, yes. But then the second factor, the gas mixing.
This is all about entropy.
Purely entropy. It's about the gain in randomness. If you have pure reactants or pure products, the randomness is low. The maximum randomness happens somewhere in the middle.
So that creates a deep U-shaped curve, what the text calls curve 3.
A very deep U-shaped curve. It bottoms out where you have the most mixing, the most randomization.
And when you add that straight chemical line and that U-shaped mixing curve together, you get the total Gibbs free energy curve, curve 1.
And the lowest point on that final curve, that's your stable equilibrium state.
And this minimum point represents what you call the thermodynamic compromise.
That is the key insight. The system doesn't just run all the way to completion, and it doesn't stop right away. It's balancing the drive to make stable products. That's minimizing enthalpy from line 2 against the drive to maximize randomness, which is maximizing entropy from curve 3.
So the reaction stops at the precise point where those two opposing drives perfectly cancel each other out.
That's the minimum. It's a beautiful compromise. If the products and reactants had the exact same stability, so delta G naught was 0, then the minimum would just be at the bottom of the mixing curve. But that's almost never the case.
So we've established that Kp only depends on temperature. But this brings up a potential confusion, doesn't it? If Kp doesn't change with pressure, why does Le Chatelier's principle tell us that squeezing a system shifts the equilibrium?
That is the perfect question to ask. And it brings us to how external conditions affect things. First, let's talk temperature. Its effect is completely governed by the reaction's enthalpy change, delta H naught.
And this is quantified by the Van Hoff equation.
Yes, the Van Hoff equation. It's incredibly powerful. It says that d ln Kp over d 1 over T equals minus delta H naught over R.
Which sounds complex, but it really means that if you plot the natural log of Kp versus the inverse of temperature, you get a straight line.
You get a straight line. And the slope of that line tells you everything. If the reaction is exothermic, releasing heat, delta H naught is negative.
So the slope is positive.
If the slope is positive, so as you increase the temperature, which means 1 over T goes down, ln Kp also goes down. The equilibrium shifts back toward the reactants, consuming the heat you just added. It's perfect, Le Chatelier.
And for an endothermic reaction which needs heat, it's the opposite. The slope is negative, so higher temperatures mean a higher Kp, pushing the reaction toward the product.
Exactly. Now, for pressure, Kp stays constant. We're clear on that. But the actual concentrations, the mole fractions in the gas, what we might call Kx, they do change if the reaction involves a change in the total number of moles.
And the shift is totally predictable.
Completely. Increasing the total pressure always forces the equilibrium in the direction that produces fewer total moles of gas. The mole fractions, the Kx value, have to adjust themselves to make sure the Kp stays constant.
So the only time pressure has zero effect on the composition is if the number of moles doesn't change, like in our A plus B equals 2C example.
In that one specific case, yeah. Pressure just raises or lowers the whole energy curve, but the minimum point, the composition, stays put.
Let's bring this into the real world. How is this used in, say, high-temperature materials synthesis? The oxidation of sulfur dioxide is a classic example.
Yes, the reaction is SO2 plus half an O2 gives you SO3. And it's strongly exothermic, so delta H naught is very negative.
So if we want to maximize our SO3 yield, our rules would say we need to lower the temperature and crank up the pressure.
And the data confirms that completely. If you're at 1 atmosphere and you just drop the temperature from 1,000 Kelvin to 900 Kelvin, the mole fraction of SO3 jumps from about 36.5% to 61.3%.
That's a huge shift for just a 100-degree change.
A massive shift.
Yeah.
And similarly, if you keep the temperature at 1,000 K, but you increase the pressure from 1 atmosphere to 10, the equilibrium again shifts toward the product side, because that side has fewer moles.
And the yield goes up.
The SO3 mole fraction goes from 36.5% to over 59%. It just shows how precisely you can steer these reactions.
And what about using gas mixtures like H2OH2 or CO2CO? Why are engineers so obsessed with the ratios of those gases?
Because those mixtures are basically the engineer's toolkit for fixing the partial pressure of oxygen at incredibly low values.
We're talking like 10 to the minus 10 atmospheres, right? Levels you could never measure directly.
Impossible to measure directly. So instead, you use a controlling equilibrium, like H2 plus half O2 equals H2O. We know the delta G naught for that reaction. And we can easily measure and control the ratio of water vapor to hydrogen gas.
And because you know that ratio, and you know Kp,
You can calculate the exact partial pressure of oxygen that must exist in that atmosphere to satisfy the equilibrium. And that level of control is absolutely critical for making sensitive, high-purity materials without oxidizing them.
so we've come full circle. From the abstract idea of minimizing Gibbs free energy all the way to the practical control of industrial furnaces.
We have, and the hierarchy is what's key. The G prime minimum is the rule. That rule is linked to the standard Gibbs free energy change, which in turn is locked to the equilibrium constant Kp through delta G naught equals minus RTLN Kp. If you get that link, you get chemical thermodynamics.
And we should never forget that the equilibrium state itself is always a compromise. It's never all or nothing.
Never. It's always that balance between the drive to minimize energy by making stable products and the universal drive to maximize disorder through mixing.
A perfect summary.
So to leave you with a final thought, just to really solidify this idea of control, remember that equilibrium means the chemical potentials are locked together by stoichiometry. So think about any system with, say, 3 reactive gases. If you, the engineer, arbitrarily decide to fix the partial pressures of any 2 of those species,
Then the third one isn't a variable anymore.
it's not. The mathematics of the equilibrium constant dictates that the partial pressure of that third species is now uniquely and precisely fixed. That's not just a cool trick. That reduction in freedom is what gives engineers total command over an atmosphere, and that is essential for advanced materials design.
We hope this deep dive has given you the foundational knowledge nuggets you needed to master the thermodynamics of reactive gas systems. Thank you for joining us.